thing.
Question, Professor. When we're finding the minimal form of prime implicants that include D, do we care about the position of where D is when reducing the expression?
Are we looking at this slide right now?
Yeah. Like for example, A, um, it's completely within X, but so we do have to care about where D is positioned.
We do have to care where D is positioned, right? So
Okay.
I don't know. I didn't put the numbers on them, but I probably should have. So you should just number those squares too. Yeah, I guess that is what is confusing. Like I didn't put the numbers on the D's, but you should, right? Because it absolutely does matter, right? So for example, the number for this first D is 9. And the number for the second D, no, it's not 9. I'm sorry. It's 12, right? And for the second D, it's 13. And for the what am I saying? No, the first D is at 10. The second D is at 9. The third D is at 12. Then 13, 14, and 15. Right. So and in fact they're consecutive, right? So it's from 10 through 15. But yes, you should number them so that it's sort of like clearer in your mind. That was the question, right?
Yeah. Thank you.
Okay, good. All right. So now I'm recording, and we're going to the next slide set, and this is it. Okay. So we're going to pick up right from that last slide from the previous lecture. Oh, yes. So while it's loading, I was telling you that using the K-maps, it's good for us visually, but it would be hard to program that if we wanted, a computer program or the computer to design circuits for you, which, is done. And to be able to do that, we're going to look later today at another less intuitive method of achieving the same result. Right? It's less intuitive for us, but it will be, better for the computer. So that's why we have to learn that. All right. So we're going to finish for the minimal forms of F. We're going to use the K-map that we came up with last time, or just now. So because all of the implicants from A through D are essential, that means that there is going to be only one minimal form. So that is, you can think about it as a rule of thumb, where if all prime implicants are essential, then there is no options. There is only one minimal form. However, if some prime implicants are not essential, that means that there is going to be variation. There is going to be different options to cover everything, and that means that that situation will cause multiple minimal forms. You can also, and then when you have the multiple minimal forms, you can think of it in terms of all of those multiple minimal forms will contain the essential implicants, prime implicants, and only some of the multiple minimal forms will contain non-essential prime implicants, right? But at least one, a non-essential prime implicant will be contained in at least one minimal form, right? Okay, very good. But in this case, there's just one minimal form. We have to add up all 4 prime implicants, and then we translate them into actual inputs. So A fully falls into X, so that was easy. Then B fully falls into Y, true value of Y, but also fully falls into complement of T. Then C also has to literals falls fully again into y and fully in complement of z. And then the last one is d. It fully forms into complement of z and into complement of t. Okay, so now let's find all minimal forms for function for f7, for the LED number 7 as the crossbar. Again, it's very similar, right? This is what you actually did have to do for today, right? So fill out the truth table for function 7, right? So 0 and 1 don't have the crossbar, 2 has the crossbar, 3 has the crossbar, 4 has the crossbar, 5, 6 will do, 7 doesn't have crossbar, and then 8 and 9 do as well, right? So, and then of course, we have our Ds for 10 through 15 for all 7 of the functions, right? Okay, so now we can put them on the K-map. So we have 2, 3, 4, 5, 6, no 7. We have 8 and 9, and no 0. Well, right, and then we have 6 Ds in the same position where they were last time. Okay, those for the 7-segment display, it's the the Ds are like always here.
Why do we include the Ds again?
We include the Ds so that we can have really big prime implicants that also cover a lot of ones, right? And if we have a really big prime implicant, like in this case, we can represent it by just a single literal, right? Here it would be just x. Right, so that makes for a really nice simplified minimal form of a function. Okay, so let's put these prime implicants on the map. So there is our biggest one, A, right, covers half the map. So now let's do more. Who can see others quickly?
Can you do the bottom 6 and the 2 in the top right? On the all the way in the last.
So for okay, first, how big is this prime implicant? How many ones or how many squares it covers?
8.
8. Okay, interesting. So the bottom 6 here, and which other
4 and 5.
And what makes you think that 4 and 5 somehow connect to 8 and 9, or how are they connected?
Flipped over or folded over and then around. Is this a torus at this point?
It is a torus, but in a torus, look, if you roll it up like this, then 4 and 5 will connect here. And then if you were to roll it up the other way, they would connect here. But no matter how you roll it up, they would connect to 8 and 9. Right? So would not. No matter how you roll this up. Right? So a torus is already rolled up in every way. But let's say that you just, we have a flat sheet of paper. So we can simulate torus by doing it in 2 steps. So first you roll it up like this and check, and no, they will not meet. And then you unroll it and you roll it up again and check, and no, they don't meet, right? So the answer for this one, no. It would be nice to have another prime implicant of 8, but no matter how you roll it up, they will not touch here. And then another way to think about it is that, look, the bottom half, so these 6, they all lie within y prime, right? But these 4 and 5, they all lie within y, so none of them are within y prime. So, if this were possible, right, this huge prime implicant would be represented simply by y prime, right? But obviously 4 and 5 are not y prime. But
Then how about the top row?
4, 6, 12, and 14.
Yeah, so both students just now had the same idea, and that's a great idea, right? So we'll do the top row. So that's good. What else?
4, 5, 12, and 13.
Yeah. Who is this? Is this Jordan?
Yeah.
Okay. Yeah, Jordan's right. Absolutely right. We roll it up like this. Oh, sorry. It's coming up right. And then I sort of jumped the gun here. Another. So we have D is also a prime implicant of 4, and then here's another one, C. And so far, all of these are essential because nobody but A covers 8 and 9, nobody but C covers 3 and 2, nobody but D covers 5, and nobody but B covers 6. So all of these are essential. Oh, and here is a non-essential one, right? But also a prime implicant, E, right? So if we roll it up this way, up, from horizontally, then we get this one more.
If we don't spot out, like for example, E, is it okay? Like,
so in this case, yes, it is okay because you actually don't need it, right? It's not as if you think of different degrees of redundancy, right? It does exist. It does count a little bit because it is not entirely within any other prime implicant. So it is a prime implicant on its own, but not only is it not essential, in the end it is entirely redundant. So well, okay, it's redundant if you have B, right? But if you don't have B, then it's not entirely redundant. So what you have here, right, is that I suppose in our minds, the sequence in which we discovered that them are important, yeah. And if you stopped with D and you didn't do E, you will come up with a minimal form, which is going to be great, right? But it's not going to be the only minimal form, right? So A, C, and D are essential, and E and B are not essential. But if you want to cover all minimal forms, right, you will have had to find both E and B, right? Because one of the two minimal forms will have B, and the other one will have E, right? So neither one is better than the other. They're equally good or equally bad. But if the question were to find all minimal forms, then yeah, you need to spot all of them. Okay. So now if we translate it, by the way, all implicants, all 5 of them, are implicants of 4, right? So that's very nice, meaning that we'll be able to represent this minimal form by sum of products of 1. So we have X. I'm sorry, is that true? No. I'm sorry. Only A is the biggest. Only A is 8. It's the implicant of 8, and the other ones are implicants of 4. So A is going to be represented just by one product of 1, and the rest of them by products of 2 terms. Okay. Any questions about this? Right, it's sort of what we already learned. We're just going over it in practice. So if there are no questions about that, just think about it again, because now we're starting like a hard thing. Okay. Okay. So the hard thing that we're starting on is called the tabulation method, right? This is a non-visual method. This is the sort of like computer-like method invented by Quine and McCluskey. The map method was invented by Karnoff. Yeah. So this is different, right? Tabulation method. So we're going to go slow here so that everybody is. Now here we see a representation of a function, right? For, let's say, it's a single bar in a 7-segment LED display, right? And it has 1, 2, 3, 4, 5, 6, 7, 8 minterms, right? So that means that out of, 16 squares on the K-map, it will have that many ones. 1, 2, 3, 4, 5, 6, 7, 8 ones, right? It will have 8 ones. And then this particular function will have 5 Ds, right? 1, 2, 3, 4, 5. So this is actually not for, this particular function is not for a 7-element display, because any function for a 7th-element display would have 6 Ds. But this is some other function. There are many situations where you will have these don't care conditions, right? D stands for don't care. So until now, you haven't seen this kind of sum of minterms representation, but it's the same thing, right? So the first half of the sum is sum of ones, right? So these are sort of minterms that matter, right? And these are minterms that don't matter, and you just OR them all together or end them up together. So before we move further, does everybody understand what this is? Yeah, it's okay to say that you don't, because it sort of like looks weird, but really it's just, when you think about the minterms of all these Boolean functions that we've seen before, they're all ORed. It's this or that or that or that, produces one. And then here we have or any of these for which we don't care, right? Okay. So now we're going to try to find out all of the best prime implicants so that we can simplify this function, but we're going to do that without a K-map, right? We're going to use this sort of like table method, right? So we start with this weird looking table where we have a row for each of these 16 squares, right? So we would have, because there are four inputs, we have 4 bits to represent this function that has the highest number here is 15, which is less than 16 but more than 8. So we need 4 variables, and a 4-variable K-map would have 16 cells, right? So instead of having K-map with 16 cells, we're going to have a table with 16 rows. And it looks sort of like a truth table. What is different about this table is that they're arranged differently, right? So far, when we looked at truth table, they were arranged in the sequence of increased binary value, right? So it was like 0, 1, 2, 3, 4. But here it's not quite like that. It's like 0, 1, 2, and then we skip 3 and 4 and go straight to 8, and then we do 3 later and 5, right? So it's the same, binary digits from 0 to 1111, yeah, that represent 0 through 15 decimal, but rearranged. Now, how are they rearranged? Well, they're rearranged in the increasing index arrangement, right? And index, sometimes represented by pound sign, in logical, not in Boolean notation. Index means the total number of ones in the binary representation. So, for example, 0, which is all zeros, its index is 0, right? But 1, 2, 4, and 8, they only have a single 1 in all of them. So the index of those is 1. Now, within the same index, we'll still put them in the increasing order, right? So all of these, all 4 of these, their index is 1, but of course 1 is less than 2, and 2 is less than 4, and 4 is less than 8. Right, so this is how we're going to arrange them, right? So then we have 3, 5, 9, 10, and 12 all have 2 1s each, so their index is 2. And then we have 7 and 14. Both of those have 3 1s. Their index is 3. And then 15 is the only one that has 4 1s, and its index is 4. Any questions about this arrangement? Okay, so all we did right now is we just rearranged them.
We will need this type of table for any tabulation question.
Yes, we will. You will need this, right? We're learning this. It will be on a quiz. It will be on the exam. Yes, you absolutely will need this. Okay. So index or pound sign is number of ones in the, if we think of it as a string, right? And the string still represents the 4 inputs, in this case X, Y, Z, and T, or whatever you want to call them, right? And this is the number of ones. And we're doing this so that it will make it easier for us to compare these strings to each other, and we'll see in a second why we need to do that. So we're going to list all of the minterms in binary and decimal form grouped by their indices. Right. So what we list here are not all possible combinations of 1s and 0s. It almost looks that way. But we're only listing the minterms, right? And the minterms are the minterms of 1 plus the minterms of D, right? So let's see how many of them we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, right? So, all combinations would be 16, but we only list in this table, the minterms for 1s and for Ds. So if we count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, right? So in this table, arranged by the index, and then within each index by increasing order, we have all of the minterms, nothing else. Okay? Okay. So they're grouped by indices in the increasing order. Now, each one of these, each minterm, or each of its representation in this table, are trivial implicants of 1. Yeah. So if you're expressing your function in the very long canonical standard form, right, you have a single implicant for each minterm for each one. But of course, that's not good enough for us, so we're going to try to find implicants of non-trivial size, 2, 4, 8, etc. Okay. And the ones, now we want to distinguish the minterms for 1s and minterms for Ds, right? So we'll mark the minterms for Ds with a little letter D. So 0, 5, 9, 10, and 14, we'll put a little D there. 0, 5, 9, 10, and 14, right? And, oops, I went too fast. The minterms, or the implicants of 1 that don't have a D next to it, are sort of true minterms that have 1s. Any questions? So 1, 2, 4, 8, 3, 12, 7, and 15 are minterms of this function that matter. And 0, 5, 9, 10, and 14 are the ones that don't matter. Okay. So now we're going to try to find, as I just said, larger implicants of size 2, 4, and greater if possible. And we're going to try to find larger and larger implicants until there is nothing else to find. And as we find implicants as we find better ones. The ones that we don't need anymore, the smaller ones, we're going to mark with a star. Right? Okay, so let's try that. Now, we can form larger implicants only by combining implicants of adjacent indices, right? So we know that from K-maps, right? You can only form, if you have some ones on the K-map, you can only form an implicant around, let's say you want to just have implicants of 2, very simple. You can form them around 2 ones that are somehow next to each other, right? Again, so we can form large implicants only by combining implicants of adjacent indices. And we're going to use the Hamming distance here to do that without a visual K-map, right? So we have this D in position 0, right? And we should be able to make an implicant from that D in any direction where there is a 1 or another D, right? And that means that in its 4-dimensional coordinates, that means that in order for it to be next to that 0, that means that only 1 digit could be different. Right? So for example, 0 and 1 could be an implicant because there is only 1 digit is difference. 0 and 2 could be an implicant of 2 also because there is only 1 difference. 0 and 4 also has only 1 difference, and 0 and 8 only has 1 difference. Right? So we're going to write them down as implicants of 2, right? It's just so this particular implicant will imply 0 and 1, this one 0 and 2, 0 and 4, 0 and 8. Yeah. And in the binary representation of the implicant, we will leave all of the digits that were the same, and the 1 digit that was different, we're going to cross it out. All right? And that means that when, if these are, some of these are, the largest prime implicants that are going to be used in the minimal form, that means that they will be represented by, for example, this one, 0, 1, would be represented by a product of x, complement of x, complement of y, and complement of z, and t doesn't matter, right? And then here, this one would be represented by complement of x, complement of y, and complement of t, and z doesn't matter, right? And then here we have complement of x, y doesn't matter, and complement of z, complement of t. Here, x doesn't matter, and we would have complement of y, complement of z, and complement of t. So any questions what we did here, right? So I want everybody.
So where we mark the ones, we're making them don't matter.
Okay, let's not use the word don't matter, but as I said, the non-prime, right? So, we mean don't matter by these, but yes, as we combine the non-prime implicants, these into bigger ones, right? Then the bigger ones become prime implicants, and the ones that they were made of don't matter anymore, and we're going to put stars next to them, and we're doing that. So you have the right instinct, so we're doing it right now. So when we put 0 and 1 together, we put star next to 0 and 1. When we put 0 and 2 together, right, make sure that there is a star. 0 already has a star, now 2 gets a star. Now 4 will get a star, and 8 will get a star. And we are done with this section, sort of, right? Now, let's see if there are any other ones that are within 1 of 0. Should we keep going and see if there are any here, any here, any there, or can we stop with the zeros?
We can stop.
Yeah, we can stop with the zeros, both students, right? Because all of the other ones will have 2 or more Hamming distance, right? Meaning that more than a single bit will be flipped, right? Like for example, here 2 bits are flipped, and here 2 bits, and then even more going for. Okay, so we're sort of done with 0, but now we need to keep going with ones, right? I mean, so with rather, right, with the 1, right? So if we look at the 1 where it's 0, 0, 0, 1, or complement of x, complement of y, complement z, and true value of t, right? Now we want to see what is right around it, yeah? So, well, 0 is right around it, but we already have 0, 1. So if we were to write 1, 0, it would be the same, right? Because, you know, these commas, they're, you know, ends. Yeah, it's like, you know, I have an apple, comma, a pear, comma, a peach, comma, an orange, comma, and a grape in my bag, right? So all of those commas, just like buts, they're also ands, right? So when we say that, oh, I have a prime implicant of 2 and it's 0 and 1, right? I could also say 1 and 0. It's commutative. It's the same thing, right? So when I came up with this one, 0, 1, and now I'm looking, oh, what's around 1? Well, and 0 is certainly around 1, right? It's just like one difference. But we already have it, right? We already wrote it down. Does that make sense? Okay. All right, so that's good. And then what else is next to 1? So 2 is not next to 1, right? Because you need 2 bits to flip. 4 is not. Also, we would need 2 bits. 8 is not. How about 3? Yep. All you have to do is to flip this second bit from the right. So we're going to put 1 and 3 here, and then 1 already has a star, and we can put a star next to 3. Okay, so what is else near 1? 5. Yep, all you need to do is flip this third bit from the right. So we get 1 and 5. We can do the same thing with 9. We'll flip the most significant bit. So we get 1 and 9. Then we have, do we have anything else? Could we do, is 10 or 12 next to 1?
No.
No. Yeah, because to make 10 or 12 out of 1, we need to flip 2 bits. So that means that we're done with ones here. So we have group, well, you know, we already have 1 and 0, and now we have 1 and 3, 1 and 5, and 1 and 9. And notice that as we keep writing down, you know, the binary, you know, form of these implicants, right? We, for example, let's look at, I don't know, 1 and 5. Yeah, for both 1 and 5, we need 0 on the right, then 1 on the left, 0 on the left, 1 on the right, 0 and 0 second from the right. Yeah, and the only difference is this third least significant bit that is represented by y, right? And we're going to cross it out. Yeah, so what we have here is complement of x, complement of z, and true value of t, and we cross out y because it doesn't matter, right? So, and we do that for all of them. So we've covered the ones. Now let's do 2's. 2 is near 0, but we already have that. 2 is also near 3, right? We just need to flip 1 bit to get 3. So we write down 2, 3, and put well, the star was already there. And then, or no, actually, we just put it there. And then 2 is also near 10, right? Because we just need to flip the first bit. So we'll put a star there, okay? And we're done with 2's. Now 4 can be next to 5. And it can also be next to 12, right? Because we flipped just this first bit. So we need to put a star next to, so 4 and 5 already have stars, but 12 didn't have a star. We have to put it there now. And then what else do we have? Let's look at 8. 8 can go next to 10, right? We just flip this bit, and the star's already there. And it can also go next to 12, where we'll just flip this bit. The stars are already there. Now, how about 3? Well, 3 can go next to 7, right, by flipping just this bit. And that's all. How about 5? 5 can go next to 7 as well, right, by flipping this bit. Right. Okay, so we marked 7 off. And then 10, where's 10? Can go next to 14.
Sorry, Professor, I kind of got lost. Like after 2's next to 10, why are we looking for 4's next to 5?
Okay, so we're actually trying to exhaust all of the adjacent ones, right? So we have, or all of the adjacent ones and t's, and we have a lot of them. We have 13. We have 13 ones and d's on a map with 16 cells. So basically, out of the 16 cells, 13 are filled with stuff, right? And we're trying to first find all pairs of adjacent ones, and we're going to have a lot of pairs, right? And then once we're done with that, we'll keep going, and now we'll try to put together pairs into squares, right? And then after that, if we can, we'll try to put squares into 8s. So it is tedious, right? And exhaustive. So first we found all of the neighbors of 0. Then we find all of the neighbors of 1, right? Then we find all of the neighbors of 2. Then we find all of the neighbors of 4. Then we find all of the neighbors of 8, right? The next one is 3. We'll find all of the neighbors of 3. Right, and then we only write down the new ones, because when, let's say, we're looking for neighbors of 3, we already have some of them, right? Which neighbor of 3 do we already have?
1.
2 and 3?
Yeah, 1 and 3, right? So actually, we have 1 and 3, and we have 2 and 3, right? So the only one that is new is 3 and 7, right? Let's confirm 3, yeah, and 7 differ by 1. So we only write down the new one. Does that make sense?
Yeah, Professor, one question I have, and I think a reason some people might be getting lost, is how do these help form implicants? Like, how do finding these adjacent neighbors form implicants?
Okay, that's a good question. Can somebody try to answer this question?
Because of like backtracking, like when we get to the end, like I just want to use something that we already have, like let's say 3, 7. We know that 7 and 3 are near one another, and then we go back up and see what 3 is also near. 3 is near 2, and then 2 is near 0, and then so on and so forth, and that just kind of groups everything together, is like, I guess.
All right, so this is your instinct, that is, good. And yes, this is what happens as we go forward. But the student is asking, and I think others have that question, is that, well, how about so far without thinking ahead, right? So the student asked, how do finding these adjacent pairs help us find implicants? So this is sort of like, it's a good question, but it's also a simple one, because the answer should be simple.
Is it similar to finding adjacent, groupings of 4 or 8 on a Karnaugh map?
Well, on the Karnaugh map, some of the implicants that we found only had 2, right? Some prime essential implicants only have the size of 2, right? And all of these are implicants of 2, right? So what's an implicant? It's when you have, what's an implicant of 2? It's 2 1s next to each other, right? So all of these are 2 1s next to each other. Like, the one in cell 12 is next to the one in cell 14, the way they're arranged. and I don't know, a 1 in cell 2 is right next to the one in cell 10, and another, and the same 2 is also next to the one in cell 3, right? So if we have 2, I don't know, 3 and 10, then we have an implicant like this and another implicant like that, right? So the answer is that all of these are implicants of 2. Does that make sense?
Okay, thank you.
So,
So these,
yeah.
Sorry, I was just going to ask, I see how we get the implicants of 2, but how can we, I guess, group them so that we can simplify the final expression? Because even if we know that we have implicants that are next to each other, connecting by one space, we don't necessarily know how they're arranged, and we could have like 2 pairs that connect in one space but are offset from each other, so they might not form an actual total of 4, if you know what I'm saying.
Right. So we just started, right? This tabular method is very long and tedious, right? And when we use Karnaugh map, we just go straight to the result. Where here, we're essentially coming up with an algorithm that a stupid but fast computer can follow to just do this quickly, right? But we need, before we write it out as a program, let's say, we need to first understand what we're doing. And that's what we're doing, right? So with Karnaugh map, if you see a group of 8, you're like, oh, great, let's circle them all and we're done. Well, the way we're doing it here, we're first going to find all of the 2s and all of the possible, right? Because you could have overlapping, like you could have implicants that are fully inside other implicants. You can have implicants that intersect with each other, right? Like none of them or most of them will not become prime implicants, but they technically are implicants. And here we're finding every single one, right? And as we keep going, it will become clear how, in the end, we will get to the same very simplified result.
so
Yeah.
let me see if I can explain it in my own words to see if I understand it. So what we're doing is we're solving the subproblem of finding all pairs of like implicants, like all possible pairs of ones.
That's right. That is what we're doing right now. Yep.
Okay. And then we're going
Right.
to combine subproblems.
Yeah. Good. I mean, I want everybody to, and just so that you understand, again, it's still, all of this could be represented by a Karnaugh map, or that is 4 by 4, right? 16 cell, squares, and because of this particular function, we have, what is it, 8 ones, right? Or half of the cells already filled with ones, and another 5 cells are filled with Ds. So most of that Karnaugh map is filled with stuff, and there is only 3 empty squares, right? 3 zeros. So imagine you have 13 full squares, and you're circling all possible pairs there. There's going to be a lot of them, right? So that's why we're seeing so many, right? So and after we looked at 3s, what's next to 3? What's next to 5? So it looks like nothing is, well, no, nothing new is next to 9, right? But 8 was next to 9, we already had it. 1 is next to 9, right? All of that is already, there are no new pairs next to 9. Then next to 10, 1, 0, 1, 0, we have 14, right? So we need to flip this second bit. And then we don't have 11. 11 is 0 on the board. And the last one here we have 12 is also next to 14, right? So let's put a star next to 14. And now we should see what is next to 7 and next to 14.
Next to 7 should be 15.
Yeah. So 7 is going to be next to 15. That's right. And 14 is also next to 15. Right? And now we can finish all of the stars. And now we put the last star. And what it shows us is that all of the ones in these were covered by implicants of size of at least 2, right? Meaning that we got rid all of the trivial, implicants of 1, right? So none of these 1s or Ds is going to be lonely, right? So they're all going to be at least in a pair. Right? So we can count them, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, right? So we have 20 implicants of 2 that cover everything, right? So if we had to name them with letters of the alphabet, you would go all the way to, I don't know, W or something. Any questions right now, right? Because
Will it always be the case where index 4 is already covered in oh, sorry, it's covered in a pair, so we don't look at it?
Well, we do sort of look at everything, right? It's just if we, like, for example.
I mean, since it's the last one, it would already have been covered with one of the previous pairs, right?
So which one, for example, which one are you looking at?
The last decimal, 15.
Okay, so what's the question about 15?
Will it always be the case where it's paired with something from going through all of the lists before it, so we don't look at that one?
That's right. Yes, yes, yeah, that's right. If you're moving, that's correct. Up the index, we have to look, eagle eye for all of them, and then once you get to that last one, then whatever was next to it, you already sort of like looked for it. You already found it, right? But also it won't hurt you to just like glance real quick. But yes, right. So 14 was, well, 14 and 7 were the only ones that were next to 15, and we already found them. Okay, good. Any other questions? Because we have to keep going. Okay, so now we have all of these implicants of 2. And now the task is, as several students mentioned as well, now how do we put them together? Well, let's see. We're going to basically try to do the same thing, right? We're going to see if we can find adjacent, right? Adjacent pairs of 1s. So, for example, in our list, we had 0, 1, because 0 is next to 1. And we also had 0, 2, right? Because, 0 is next to 2. And we had a bunch of other ones. But we also had this ones. We had 2 and 3 together, right? Because 2 is next to 3, right? And for example, with 0, 1, 0 and 1 are the same, with the only difference of t, right, the last bit. And 2 and 3 are the same also because of the difference in the last bit, t, right? And because that is the only one difference, right, we crossed it out, right? So now we're going to look at these binary representations and again find another one with the distance of 1, Hamming distance of 1. So for example, when we look at 0, 1 represented by 0, 0, 0 crossed out, right, we want to find another one that differs just by 1. So for example, 0, 2 differs by 2, 0, 4 differs by 2, 0, 8 differs by 2, 0, 1 differs by 2, 1, 3 differs by 2, 1, 5 differs by 2, 1, 9 differs by 2, right? But 2, 3 is actually very similar to 0, 1, right? It starts with 2 zeros, ends with crossed out, and the only bit that is different is the second bit from the right, right? So that tells us that 0, 1 is going to be fully adjacent to 2, 3. Right? Another way to say
Repeat
is, let me just and then you ask your question. So another way to say it is that the distance is, the Hamming distance is 1 among the bits that matter, right? The one that was crossed out doesn't matter, right? Because they're already next to each other. And then the difference between the remaining 3, 0, 0, 0, and 0, 0, 1 is just 1. Okay, your question.
Oh, could you repeat like the first part? Why is 0, 1 adjacent to 2, 3 again? Is it because of the Hamming distance being 1?
The Hamming distance being 1, right?
Okay.
So we want the short, we want, whenever we have a string of 4 bits, right? We have a different Hamming distance of 1 means that they're adjacent. Right? Same thing is true with pairs, right? A Hamming distance of 1, you just compare this string to any of them, but you will only get so far the Hamming distance of 1 here, right? 0 and 0 the same, 0 and 0 the same, right? 0 and 1 are different, and then the last one doesn't matter, it's crossed out, it's also the same. Okay. And then if we keep going with 0, 1, when we get to 4 and 5 here, right, again, we get Hamming distance of 1. It's difference in this bit. So we're going to write down 0, 1, 4, 5. Right, and then when we get to 8, 9, if we're still comparing 0, 1, right? We get to 8, 9, and again, this is the only bit that is different. So 0, 1 is going to be next to 8, 9. Right? And as we do this, now we're writing down implicants of 4, right? So these are, these are either squares or long bars, right? They can be adjacent. They have to be fully adjacent, but could be adjacent on any side. They can be just like in a Tetris. They can be like staggered, right? They have to be. Okay, and so we have 3 implicants where it's 0, 1 adjacent to something. Then for 0, 2, the only one that it's going to be adjacent to is 8 and 10, right? So 0, 2 has 0, 0, dash 0. Here we have 1, 0, dash 0, right? So just the leftmost byte.
Well, it's also adjacent to 1 and 3, but that's already covered.
That's right. Which one is adjacent to 1 and 3?
0 and 2.
Yeah, right. So let's look at that. 0, 2 is 0, 0, dash 0. 1, 3 is 0, 0, dash 1, right? So again, it's adjacent to it, but why do we not write it down? As the student said, we already have it, right? Because to say 0, 2, and 1, 3 is the same as saying 0, 1, and 2, 3, right? Because it's commutative, you're simply describing the cells on the Karnaugh map, and no matter in what order you list them, it's still the same cells, right? It's the same square. Okay, so then we keep going, 0, 4. The only new one is going to be 8, 12, next to 8, 12. So once we find pairs for these implicants, we're going to mark them with stars. So it looks like now we took, I don't know, there's almost a dozen of these, right? And they all are now covered by these 5 implicants of 4, right?
Is there a reason why we mark the star to avoid repeating them? Or
No, you cannot avoid repeating. Oh, 1 second. To put a star to avoid. Not really, right? I mean, as I said, this is a tedious and exhaustive method. And, to computer, it doesn't matter because it's so fast, right? So basically, every time you have to check all of the ones beforehand. Okay. Note, every size 4 implicant will be formed in 2 ways out of 2 size implicants, right? So for these 5, right, you will have encountered them twice, right? But that's fine. Yeah, you just, obviously you don't repeat them. Now, why is that the case? Well, for example, if you have 4 ones next to each other, your implicants of 2 could have been, horizontal like this, right? And then also the same 4 ones now will be covered by a single implicant of 4. Right? But then you also had, not could have, you had, right, somewhere in this list, the same 4 ones now covered by 2 like this, but then those 2 will produce the same implicant of 4. So this is sort of the visual explanation of like all of the duplication, but then it sort of resolves itself. Right? And that like indirectly answers the questions before, is like, oh, like how do having these, implicants of 2, all of them, redundantly over and over, how is it helpful in the end? Well, it is, right? Because as we try to put them together, they will, get rid of the redundancy, and now we have fewer, big implicants. But we're not done yet, sort of, right? But so far, sort of makes sense, right? So now we'll look at the additional implicants that where we compare with 1, right? So if we have in the group, in this group, right? So we start with, let's say, with 0, 0-1, so it's 1, 3, and as we keep comparing them, the one that it's going to be next to is 5, 7, right? That's the only new one that we get, because it doesn't have a star yet there, so we get 0, 3, 5, 7, and we'll put a star there. I'm sorry, what about? Yeah. What did we have? 3, 7. Okay, so it's the 1, 5, 3, 7, right? So 1, 5, and 3, 7 are next to each other. The only difference is this.
why did we put a star next to 3 and 7? Is it because it's in the big?
It's 1, 5, and 3, 7, right? 1, 5, 3, 7, and then also 1, 3, and 5, 7. It's I think I should have put this. I should have put those stars in the different order. The 5, 7 should have been first, and then 3, 7, and then 10 and 14 are next to 8 and 12, right? So 8, 12, and 10 and 14 make up n, 10, 12, 8, 10, 12, 14. And then, yeah. And then, so far now we have 7 implicants of 4 that covered all of these, right? And then, we only have 2 left here that we can see they're not next to anything else, so they will not get stars, meaning that we cannot discard them. What does it mean that we couldn't discard them, that they're not next to anything else?
Does that mean they're prime?
Yeah, it means that they're prime, and also, well, and also that they're
Or
essential.
essential, sorry, yeah.
Yeah. No, both. They're both, right? That means that you know, whatever we end up with, we'll have those in our final formula. We'll have like a little implicant of 7 and 15, and we'll have a little implicant of 15 and 14, right? So we cannot you know, get rid of them, because then they're not next to any other pairs that we can, you know, nicely circle. Okay, so we stop when we can no longer form larger ones and name, and at this point we name all of the unstarred ones as prime implicants. Note, we can form larger implicants only by combining implicants of adjacent indices, right? So we actually have a lot, right? To minimally express this formula, we ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9 implicants, right? So there is 9 prime implicants. And now we just give them letter names, yeah, from A all the way to I, right? Okay. Any questions right now? No? So this was a really long and slow way to get to the point on the K-map where we just simply circled a bunch of prime implicants and gave them letter names, right? So that's the result. So I'm going to assign homework, but before I do, let's look at this some more. Ask me some questions, yeah.
We still also have to keep the 2 prime implicants that are not part of the bigger one, like 7, 15, 14, 15, right?
Yeah, we still have to keep H and I, right? Because why? Because if we look at these, right, at A, B, C, D, E, F, G, the nice big ones, implicants of 4, you will see that none of them cover 15, right?
So those will essentially be essential implicants.
Well, no, they're like, as Patrick said, they're prime implicants, right? So, but they're not essential because either H or I will have to be in at least one of the minimal forms, right? Because without them, 15 is not covered. So whatever other combination you choose of the prime implicants, one of them will need to have I. At least one of them will need to have I, and at least one of them will need to have H, right? So that means that they're prime, but not essential. Essential means that all minimal forms will have them. Right? And that means that with this tabulation method, you get all of the prime implicants, whether they're essential or not, meaning that any of these prime implicants, all of them, starting from A through I, will be in at least one minimal form.
Is there a way of maybe identifying if any of them are essential implicants, or are they only prime and we can't really figure that out unless we like draw a K-map?
For now, we will stop with the Quine-McCloskey here, right? But yes, you know how to figure it out on K-map just by looking at them, right? So here with the tabulation method, you know, it's going to be, you know, again, like sort of like exhaustive search where, let's say you to find the essential one, you need to find one that has a square that is not repeated anywhere else, right? So, for example, just, you know, looking at it, I'm having trouble.
E has a 9, but I don't think there's anywhere else.
Okay, very good. E has a 9 and nobody else has a 9, right? So that would make E essential, right? I think that none of the other ones are in that sense essential, but in order to come up with a minimal form that covers, all of these squares, you will need a lot of them in each minimal form, right? Because you do need, you will need at least an H or an I, right? And let's say that if you took an I, then you will need to have another one that covers 14, and that means that you will need to have an A, right? So it's sort of like a chain reaction. So you will have a fairly long combinations of these prime implicants, and all of your minimal forms will have E, and then, some of them will have, certain other implicants, and some of them will have certain other implicants, right? So there will be.
When we reach a step, we just draw the K map and then find the minimal form like usual.
So for now, without covering anything else, I will not ask you to do that last step. For now, let's learn this, the tabulation method up to this point. And this point is identifying all of the sufficient prime implicants, right? Let's say that if you want to do the last step of identifying the essential one, literally, look at, let's say, one by one. Let's go from, starting from here. This one has 7 and 15. Do we see 7 and 15 somewhere else? Boom, 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 boom. We see do we see 7 and 15 somewhere else, right? So we see 15 right here. So, okay, found it already. Now let's see if we see 7 somewhere else, and there we see it. So we found both 7 and 15. That means that I is not essential. Now let's go to H. Well, already 15, somebody else has 15. How about 14, right? A has 14, so H is not essential also. We have 1, 2, 3.
I think 9 is the only one.
I'm sorry. Yeah, and if you go like this exhaustively, and that is what the computer would do, it would, you would find that E is the only essential one. That means that this particular function will have many minimal forms, right? But all of them will have E and some combination of the other ones. But again, for now, I just want you to understand and be able to put together this table to the point where we have a list of all prime implicants. So we still have just a few minutes left. I want to explain the homework, and then I will also give you sort of like thinking homework, where you don't need to actually write anything, but I want you to think of something. Okay, so the homework that you have to do, consider the function on which we applied the tabulation method. Like, this is the function that we just worked with. This is the same thing. So now I would like you to draw, right? It's this same function, right? We're still working with this function. So now I would like you to do two things. First, draw the K-map and circle all of the prime implicants, right? As I think Stephanie or Anna was saying, now that we have them, let's, just now put them on the map, these from A through I, right? And then you'll see them on the map visually, okay? And label them, with the same letters as we just did with the tabulation method. And now that you see them on the K-map, now minimize it, right? Now come up with the shortest possible formulas, right? And we know that all of them will have E, but right, we don't. It will be easy to see on the K-map, which ones will be shortest sufficient combinations. Okay, so this is the assignment. So the first part is just to draw it on the map, and then 2 is to actually come up with the shortest with the minimal forms, right? And you will have, well, at least 2 of them, maybe more. Any questions about this? Okay. So now the other part of the homework that you don't need to write or submit, but you need to think about it because it'll help you with an unannounced quiz that might happen on Monday, is moving away a little bit from the abstract, ones and zeros, and what we're doing here is think about what. So think back to logical operators, right? We have the essential ones, the and or and not, right? And then we have the compound ones like NAND and NOR and XOR, right? So think about what it would take to make a circuit for an operator that meant majority, right? We call that a majority Boolean function, a majority Boolean logic. Like, so for example, if you have a multi-input, there was something else. Let me show you just one more thing. This is, again, going back. So earlier, Mohammed mentioned that, I prefer using, this method of drawing K-maps, right? And this is, so instead of, the way I like it with the, chopping things in half where it's x, x prime, y, y prime, right? This is the textbook method that you should also be familiar with, right? Because I do assign you textbook readings, and this is also a neat method that makes it easier to identify the numbers of squares, right? So instead of x, y, z, t, they use a, b, c, d, same thing, right? And so I say, oh, okay, so the bottom half is A and the top half is going to be A prime, right? And then the middle stripe is B and the top and bottom are B prime. Or here it's the right side is C, the left side is C prime, right? But that allows you also to sort of like assign bit values, right? Where on each side you'll have pairs. So on the vertical you'll have the least significant 2 bits, and that here you have the most significant 2 bits, right? So, I'm sorry, the other way around. These are the most significant 2 bits. Oh, what did I say? Yes, no, I was right first. Least significant 2 bits, most significant 2 bits, right? So that means that the address of this cell is going to be 0, 0, 0, 0, which makes 0. And this one is going to be 0, 0, 0, 1, which makes 1. And then this one is going to be 0, 0, 1, 1, which is 3. And the last one is going to be 0, 0, 1, 0, which is 2, right? Et cetera, et cetera. But this is just another way of working with the K-map, right? But this makes it sort of quicker to number the cells, as it were. Okay, any questions about this? So this is in the book, in the PDF book that you have, and I'll post these few slides from the publisher slides also. Again, any questions about this? Right, this is just a note on notation of K-maps, and now back to what I was talking about. If we look, just hang on, don't leave yet. This is sort of important for Monday. So these are from the publisher slides that I already posted before. Mana is the publisher. If we look, okay, for example, let's look at this one. Yeah. So here we have a 3-input AND gate, and here we have a 6-input OR gate, right? And the way they work is that for a 3 or 5 or 20-input AND gate, what does it mean? Can somebody just quickly tell me? Let's say here we have 3 inputs, A, B, and C. How many of them need to be true in order for F to be true?
All of them.
All of them.
All of them, that's right. Like normally, AND gate has two things going into it, x and y. You know, for it to be true, both x and y have to be true. But if you have 3 or 30, right, an AND gate, still an AND gate, all of them have to be true. Right? Now, what about an OR gate? In this case, we have OR gate with 6 inputs from A through F. How many of them need to be true?
Only one.
Just
At
one.
least one.
Only one. Just one, yeah, just one. So what I want you to think about is what is called the majority function. That, and in some ways outside of Boolean logic, that is very intuitive. It's neither, it may not, you know, it's not the and it's not the or, it's something else, right? It's something that is, you know, however many inputs it has, it will be true if most of them are true. And it will be false otherwise. That's one way of thinking about it. And if we think about it this way, then what happens in a situation of tie, right? Let's say we have a majority function with 6 inputs, A through F, and 3 of them are true and 3 of them are false. So a majority function that I defined just now, would it be true or false if 3 of them are true and 3 of them are false?
True.
True. Well, without me being sort of like specific by what I meant by the majority, if we have half and half, if it's an even number of inputs and half of them is true and half of them is false, then we have a tie, right? And a tie needs to be resolved somehow. Now, as it happens, the way I defined it before, where I said that it's true if it's a majority, otherwise it's false, right?
Then it would be false.
Then it would be false, right? So if it's defined like this, strictly, then a tie means false. However, it doesn't need to be defined that way. So there are majority functions that have, well, random tie breaking. That's something else. But what's a third possibility for tie breaking, right? So the first possibility is where I just said it. If it's a tie, it's no, it's false. Another possibility, there is some kind of random tie breaking. What is the third possibility that we can do with the tie conditions? It's sort of a trick question, and it's similar. The answer is going to be related to what we've been working with D's on the K-map.
That it doesn't matter?
Yeah, we could say that, oh, we don't care about tie conditions, right? It's just like they don't matter, right? You know, if it's true if it's majority, it's false if it's minority, and if it's a tie, we don't care. So that's another person. Anyway, so just, I don't know, maybe think a little bit about how you would, you know, implement a majority function. And of course, you know that a circuit for a majority function cannot be universal. It cannot be universal for, you know, n number of inputs. You know, any majority function will have a specific number of inputs. So for example, you have one majority function for 3 inputs, and you know there is no tie possibility. Or you have a majority function for 6 inputs, and there is a possibility of tie. Anyway, just something to keep in the back of your mind. You don't need to actually do anything. I mean, just, you know, to think about what it's that such thing exists.
So to cover again, you have a tie when you have a 1 and a 1, or 1 or 1.
Well, so if you want to have a majority function with just 2 inputs, is that what you're asking?
Or I mean, when do you have a tie with the inputs?
So with majority functions, you can only have ties when you have even number of inputs, like 2 inputs or 4 or 6, right? If you have an odd number of inputs, there is no possibility of tie. So you will always either have majority or not, right?
Okay. When you say number of inputs, do you mean the number of inputs that are 1?
No, total number of inputs. So like here we have an AND function and an OR function, right? These are just like straight up AND and straight up OR, right? And this AND has 3 inputs, A, B, and C, and this OR has 6 inputs, A, B, C, D, E, F. Now, instead of having an AND, I actually don't remember what the picture is for majority. Let's try to Google it. Logical majority operator. I don't know if there is an operator. Yeah, there is really no there is no like visual. Is that? Yeah, the whole point is that you have to make it, right? There is no such thing, and it's going to be different for any number of inputs.
Because the way I'm picturing it is like for example, we have an even number of inputs here, 6, right? If
Yeah.
A, B, C, and D are 0, then the majority of it is 0. But if A, B, and C are 1 and D, E, and F is 0, that's a tie. But
That
then,
is a tie. Yeah.
and then if A, B, C, and D are 1, E and F are 0, then that's a 1.
Yeah, a majority of any of them. So right, so here you have 6 inputs. If any 5 or more of them are 1s, then it's true. If any 5 or more of them are 0s, it's false. And if it's exactly 4 1s and 4 0s, no matter which ones, then it's a tie.
Okay.
Right? And then here, where we have just A, B, C, then again, it's unequivocal. It's either going to be a majority of 1s or a majority of 0s.
Wait, wouldn't the tie be if any 3, not 4? Because half
Yes,
of
yes,
6.
yes. Yeah, you're right. I misspoke. Right. So 3 and 3 would make tie here. Yeah, for some reason I thought there are 8 of them. There's so then 4 1s, 4, 5, and 6 1s make a 1. 4, 5, and 6 zeros make a 0. 3 and 3, 3 zeros, 3 1s make a tie. Right, but of course there is no tie. There are no ties in real life, like in logic, right? It will have to be either 1 or 0, right? So 3 possibilities for that is that we say the tie is a 0. That's one possibility. Another possibility is that we have some kind of randomized engine for resolving ties. And the third possibility is we say we don't care, right? Meaning that we're going to prioritize something else. We're going to prioritize the simplicity of our circuit, right? We want to make the simplest and the cheapest circuit, and we don't care if that circuit will produce a 1 or a 0 in a tie condition. Yeah. So when you think about it, don't think about random number of inputs. Think of small, like 3, 4, no more than 4. Okay. Okay, that's all. Again, the actual homework that you do have to submit is this, right? In fact, why don't you take a screenshot of this right now, just so that you. Yeah, please, everybody, take a screenshot. I mean, I will post it, but just so that you can work at it right away. Yeah, so that you can just continue from what we were doing here. Right, what we were doing, we were just looking at the Quine-McCluskey tabular method. Now we found the prime implicants, so now you're just going to put those same prime implicants on a K-map, and once you see them, you'll be able to come up with minimal forms easily, visually. Okay, any questions before we say goodbye for the weekend? I promise to publish the midterms grades hopefully later tonight. I'm playing with weights for questions so that it's a good grade distribution. What was the question? Hello?
I was gonna ask if you can stay for office hours for like 10 minutes maybe.
Oh, for sure. Yeah, absolutely. Anybody else needs to talk to me? Yeah, so what I'm going to do is I'm going to sign out of here, and I'm going to create an office hours session right now. You'll see that it will be called, when you refresh Blackboard, it'll be called office hours now, and you'll be able to join. Okay, so I will see the student in 30 seconds in that other session. Okay.